So our next actual, I think we have our next guest. Very excited to have her on the show. This is the March 2016 issue of Science News cover story of gravitational waves. And so let's have a big hand for Dr. Laura Cottonati. Did you see my Albert Einstein action figure?
I have one of these in my office.
Awesome. All the cool people have one. New in box?
No.
Ah.
It's comfortably sitting on a bookcase. Next to the Coke bottle that says Einstein.
Share a Coke with Einstein.
Yeah.
Very nice.
See, most people think about it as a box of Play-Doh.
Yeah.
That's an anti-social thing.
This is Albert.
There you go.
I'm a little intimidated just to rip the plastic.
I actually braided his hair.
There you go. You're kind of making him more like Manu every day. So, Laura, of course, you're part of the LIGO team, right?
Yes.
And can you tell our audience a little bit about, just briefly, what is LIGO? And what did you just feel that? Did you just feel that gravitational wave?
Gravitational wave? Boy,
I
you're
could
good if you can feel that.
I felt, maybe it was my imagination. What's LIGO?
So LIGO is two things. So LIGO is the Laser Interferometer Gravitational Wave Observatory. It's a mouthful. It's a detector for gravitational waves. It's basically we're using lasers to measure changes in the distance between mirrors that are 2.5 miles apart. And these changes are due to the passage of gravitational waves that are produced by astrophysical events that happened many, many, many years ago. So we have two such detectors. One is in Louisiana and one is in Washington State. It's a project funded by the National Science Foundation. LIGO is also a collaboration of about 1,000 people that are scattered around the world. So US, but also in Europe, in Asia, Australia. And all together we've been working to bring these detectors up to the point where we could announce on February 11th the discovery of gravitational waves.
That's awesome. Now, as I was telling Laura backstage, I think the progression is Galileo, who gave us the optical telescope, right? Light. And then we have radio telescopes. And now we have an entirely new way of observing the universe. So Galileo, Marconi, Cottonati.
Yeah.
Could you write a song about that? All right, excellent. We'll work on that.
It's the Italian legacy.
That's right. So the Italians know a lot about the universe, apparently. So seriously though, this does give us a new way of observing the universe.
Yeah, so there are two exciting aspects of this discovery. One is that we proved Einstein right again. We also proved him wrong because when he predicted gravitational wave 100 years ago, he thought there was no way there would be any event that would produce anything remotely detectable. And so, we got him right and wrong at the same time. It's quite an achievement. But also now, gravitational waves are going to be this new signal, this new sense on the universe. It's like when you can see and you can hear the universe. So this event that we found, this is something that happened 1.3 billion years ago, so far, far away. And we could basically hear the sounds that the two black holes did as they merged.
Yeah, so that's amazing, right? I mean, we actually have audible evidence of two black holes colliding here in 2016.
You want to hear what they sound like?
Yeah, dude.
I was guessing.
Okay, wait, this is the first impression.
Okay.
Black holes colliding. Ready?
Okay.
That was impressive. That was it.
Oscilloscope, and that's it, man.
Yeah.
I can
Right.
tell it.
Yeah.
Because what's happening is they're rotating, right, and they're getting
They
closer
get
and
faster
closer.
and faster, and so the frequency of the wave increases up until the point the horizon clash, and so then at that point the two objects merge, and we get a black hole And then the black hole is excited and it de-excites, so you get.
So what we're actually hearing are the actual ripples in space and time, right?
Yeah,
The
yeah.
fabric of space-time?
Yes.
And
yes.
that's, I guess, I've heard that called one of the stiffest substances around, so
That's right.
it takes a lot of energy to make that ripple.
Mhm.
How much energy was released in this collision?
Septillions, septillions, gazillions.
Gazillions! We're inventing new numbers.
The amount of energy, so we had two black holes. They were both about 30 times the size of the sun. And as they merged, they created a black hole that was a little bit smaller than the sum of the two. So we had the equivalent of 3 suns, so the mass of 3 suns. Einstein tells us E equal mc squared, so we get the mass of 3 suns converted into energy. That energy is deployed in a fraction of a second. And so the power that was emitted there was equivalent to 50 times the power of the visible universe. And it was just this blast. This blast that was produced at that point. Now, as one of us being nearby, the gravitational wave would have been so strong that we would have been stretched, twice in size and then
Wow.
squashed down.
Who just
So-
fell down when he heard the news?
but then these waves traveled for 1.3 billion years at the speed of light, and they finally eventually reached Earth. And the effect here was over the length of the detector, which is 2.5 miles, it was equivalent to 1,000 times the size of a proton. So something so small that we have to fight with quantum mechanics and
Yeah.
super small.
And this was one of the reasons Einstein was very doubtful that we could detect
That's
them.
right,
Because-
because you need something very powerful.
Right.
And then something very, an instrument that can detect at those limits.
Right, can
which-
detect a fluctuation,
Yeah.
the thousandth of a proton.
Which
in-
up until 10 years ago, people would have told you, yeah, no way, that's gonna happen. So,
But I mean, with nerds like us, you're preaching the choir. We're excited about this thing, right?
Good.
As Lou was in the turn of the last century, when I had general and special relativity. But I mean, what does this mean to the
I've been
average
traveling very
person
fast, that's why I look so young.
who's not excited? What does this mean to the average person?
Well, so, if one thinks about immediate applications, so things that you can use, well, these detectors are really miracles of engineering. So
Right.
there has been, in building them, lots of development in laser science, control systems, so all things that will have repercussions from the technology point of view. When Einstein came up with general relativity, he didn't know back then that we can now have GPS that can track,
Right.
how we go to Starbucks, So the repercussions of fundamental science are on a longer time scale. But to me, what's most important is that really, this is my Italian heritage, I guess, that's the Galileo heritage of, you're just observing the unknown in a new way. It's kind of part of the legacy that we are giving to the next generations. It's we're going to be able to learn more about black holes, and at some point we may know more about even the Big Bang. So where do we come from? Because the gravitational wave are going to tell us information from earlier than we can so far.
Right.
So it's all part of the quest for knowledge and discovery. And that's what I find is the most enriching
But
part.
admittedly, I mean, it was about 75, 80 years between relativity at the beginning of the last century and the fact that we use them as corrections in the satellites for GPS. So I think you got some time.
Your time, yeah, we'll come up with something.
Part of the century.
Yes.
Absolutely.
Yeah.
All right, well, let's have a hand for our guests. Laura